I was actually
One day.
All right, doesn't sound like I'm hearing much talk about the sun right now, so let's go ahead and get started. Leia, you can thank David Chow, he wanted us to for you. So, David, what is with the sun?
It's composed 97% of hydrogen, and then what happens is the two hydrogen molecules will combine, forming helium and releasing energy.
Okay, so that's a whole lot of detail. Anybody else wanna? Yeah, Nick.
Due to that, if you spray water on the sun, it'll actually get hotter.
If you spray water on the sun,
Like to try and put it
the
out.
sun will get hot.
Yeah.
It sounds like you've heard that somewhere. Where did you hear that?
Read it somewhere.
Is it video? I heard it somewhere.
Okay. That just sounds very odd. I don't know that I physically disagree, but
you're adding more.
I don't know how
Yeah,
you would
like,
get
yeah,
the vessel that would have the
Oh,
water
yeah,
to
that would
the
be
sun
hard.
without. So the sun probably won't come up too much today, but it's gonna be like the prime point of our final 20 minutes on Friday. All right. So our objectives for today. I do have a holdover. No, I don't have a holdover. So this is a new one. Draw and annotate a graph showing the variation with nucleon number of the binding energy per nucleon of our nuclei. We want to solve problems involving mass defect and binding energy, so we've already been doing that. We want to describe the processes of nuclear fission and nuclear fusion. After we do that description, that's where we'll kind of break, right, do our final two presentations, and then we'll come back and we'll use this graph to quantify how much energy gets released during a fission or a fusion. All right, and then we might want to spend just a tiny bit more time with that on Friday. All right, so here is this graph that we need to be able to sketch and annotate. So on the x-axis, and something very similar is on page 7 of your topic 7 packet. That would actually be a great thing to have in front of you, so you don't have to try and read values from this. I think it's page 7. If it's not page 7, it's right around there somewhere. It might be like page 10 or so. Oh, it's actually page 11. All right, so it'd be very helpful to have page 11 of your packet open like for the next 30, 40 minutes. All right, so in the one in the notes, the x-axis is labeled mass number. On the one in your topic 7 packet, it's labeled nucleon number, same thing. Right? It's a number of nucleons. And then on the y-axis, this is called binding energy per particle. In your topic 7 packet, it's called binding energy per nucleon. That's probably a better name for it. All right, so we have a bunch of data points, and then we kind of have, it's really kind of connect the dots, but it's smooth curves in some places. But we are seeing, how the binding energy per nucleon varies as we get to bigger and bigger nuclei. So one extremely important thing to recognize is that this blue region, it's kind of the ones with the largest Y values, those are the most stable nuclei that are on here. Right? The largest binding energy per nucleon means we have to do the most work to pluck a nucleon out of that nucleus. Okay? If we have to do the most work, that's because it's very stable. Right? If it wasn't stable, it wouldn't take much work to pluck it out of there. So the ones up here are the most stable nuclei. We have a fairly steep increase in stability as we go from the very small mass nuclei, up towards that region. It does kind of get a little flatter as we get kind of close, but it's very steep at the beginning. It's a lot more gradual, right, on the heavier side of those most stable nuclei. So the objective said we need to be able to sketch and annotate. All right. So the sketch would probably look something like that. And then the annotate, I think, could be as simple as just putting a few isotope indicators on it. So the most stable nucleus. Now I think that was your question when you came in on Thursday. Wait, did I see you Thursday? That was like the kind of flip. Yeah, I did. But whatever. At one of the last classes, I think I asked what's the most chemically stable element, and I asked what's the most stable nucleus. Does that sound familiar, or was that?
It does.
Now, did we say what the most stable nucleus was? Did we say what the most stable chemically wise element was? We just never revisit. Okay. So what's the most stable? What's the most chemically stable element? Right. You have your periodic tables in front of you. What's the most chemically stable element? Yeah, Cliff. Cliff says helium. I heard somebody say hydrogen. Hydrogen, I would say no. Hydrogen is actually very reactive. Elizabeth? Iron. Well, out of those three, I would definitely go with helium. Right? Isn't that whole column, the noble gases, they're called noble because like they don't give up any electrons, and they don't receive any electrons? Why am I getting such blank stares? Right, the noble gases have that full octet of valence electrons, so they really don't do chemistry. There's got to be something there. I don't know if it's helium or whoever's at the bottom, but chemically it's going to be one of those. Now, nucleus-wise, right, most of the figures that I see do indicate an isotope of iron as having the largest binding energy per nucleon. I have seen some, though, that identify an isotope of nickel as being the most stable nucleus. So whatever, like one of those, if we can label our peak with one of those, that sounds pretty good. Uranium is the largest relatively stable nucleus, so we can annotate our binding energy per nucleon graph with uranium. And then if we really want to show off a little bit, we're actually gonna alter this sketch and show this peak at the beginning. And we're gonna annotate this guy. Who's that? That's our alpha particle, or our helium-4. That's right. Right. Remember, the whole reason we have this alpha decay is because 2 protons and 2 neutrons is a very stable arrangement of nucleons. All right? So that alpha, or that helium, whatever you want to call it, is very stable. Right? It doesn't follow the trend that we see in the other places. 2 protons and 2 neutrons is extremely stable. It's a very, almost perfect amount of strong nuclear force for the electrostatic repulsion. All right, so to sketch and annotate, I think what I have up here would be probably more than sufficient. Yeah?
Would we need to label the y or x-axis and give values?
Well, sure, if it's not there already. Oh, label yes, values no.
Okay.
Label yes, values no. So it's binding energy per nucleon on the y-axis, and then mass number, nucleon number, number of nucleons, whatever, on the x-axis. Follow-up questions from anybody about sketching or this level of annotation for this graph? All right, let me ask a follow-up question before we move on to fission and fusion. Which nuclei up here has the largest binding energy? I'll ask that again. Which nuclide up here has the largest binding energy? Right? Don't talk in your foursomes, but take 5 more seconds and be ready to answer that. Who has the largest binding energy? Raise your hand if you're pretty sure you have the right answer, because it's obvious. All right, a few. Only about 6 of you. Justin, what is it?
Uranium,
Ooh, Justin's right. Uranium. Tell us why you said that.
because uranium has 238 nucleons.
It's got the most nucleons, right? It doesn't have the highest binding energy per nucleon. It's at about 7.2 mega electron volts per nucleon, right? Iron and nickel are like 8.5, 8.6, but it's got more nucleons. It's got the most number of nucleons, so it does have the highest total binding energy. Follow-up issues with that. I've seen questions that very smart students that know their stuff got wrong, right, like that. Biggest binding energy, highest binding energy because it's the biggest. Can we use, no, we can't use that. Is the alpha particle pretty clearly displayed on the page 11? Great. Can we take 30 seconds and use just this figure on page 11 to calculate the total binding energy of the alpha particle? Okay, 30 seconds, total binding energy of the alpha particle. Hi.
Do you have to know my topic 7 packet?
I do, I just don't know if I put a grading for you yet.
Okay.
So why don't you actually look on with Shankar? Or Shankar isn't that busy, is that not right? Why don't you look on with Shankar? Anybody done yet? Like some of the same people that just had their hand up. All right, so we can look from the graph And I am noticing some discrepancies between this one and that one, right? On here, the binding energy per nucleon of helium looks like it's about 7.1 mega electron volts. On here, it's about 6.9, 6.8, so that's kind of interesting. But whatever, I said to use this one. So we have 7.1 mega electron volts per nucleon, and then we have 4 nucleons. So what is that, 28.4? So 28.4 mega electron volts. Now, we could have calculated this last class. If I gave you the mass of the nucleus, right, we could have subtracted that from the mass of the 2 protons and the 2 neutrons, right, subtracted that, and if we had the right units, multiply it by c squared, but we should get the same answer as this, all right? So if you have this chart, then calculating binding energy is pretty darn simple, right? If we don't have this chart, then we have to do the long way with the mass of the individual protons and neutrons. All right, follow-up issues before we move on to fission and fusion. We will come back to this graph later. Follow-up questions right now. Fantastic. So we're going to take a few minutes and describe fission and then fusion, right? And then we'll come back and quantify the energy release with those using the chart that we just looked at. All right, so fission is where we start with a pretty big nucleus and we split it into 2 smaller nuclei. If fusion is the opposite. We have 2 smaller ones, we jam them together to create a bigger one. Now, fission should be producing like daughter products that are of fairly similar size. All right, so what are we doing here? Here we have a uranium-235. Who are we shooting into it? Well, it's a single particle. An electron, I don't think so. In fact, we know it's a neutron because in like step 2 of this cartoon, we see a fuzzy uranium-236. So it must have been a neutron that we shot into it. And that's because neutrons are pretty easy to get into the nucleus. We talked about that when we did artificial transmutation. We said a neutron's a very effective thing to promote instability because there's no like repulsive force. So we shove this neutron into the uranium-235. We kind of temporarily get a uranium-236. This uranium-236 is extremely unstable. That's why the edges are all jagged. And then we end up with a krypton-92, a barium-141, and 1, 2, 3 extra neutrons that get shot out of the nucleus. So we do have 2 fairly similar sized things. They're not identical, but they're fairly similar size. So this would be a fission. And we typically do promote a fission by using a neutron. We also either always or almost always get extra neutrons to be released as a result of the fission. And I'll come back to that momentarily. But I think we always get at least 1 neutron spit out as a result of that. Cliff?
Does it always produce like the same 2?
It absolutely does not always produce the same 2, and that's a great point that we're going to come back to next also. So not the same 2, not always krypton and barium, but they are going to be 2 roughly equally sized things. Yeah. Other issues right now on fission just meaning that we're starting with something big, right, hitting it with something, and then getting 2 smaller things as a result. Great. So on the next slide, I have a drawing which does fit into the sequence that we just looked at. In fact, 95% of the time when we're talking about fission examples, we're using the fission of uranium-235. Right? And the main reason for that is that's what we use in this country in our fission nuclear power plants. There are nuclear power plants that use a plutonium isotope, I think plutonium-239, but we don't do that in this country. So almost all the examples we look at are uranium-235, including this one. So here, well, who is this right now? Who is this right now? It's not uranium-235 anymore. Who is it?
2 protons.
I don't know. Is it 2? Looks to me like it's still 1.
Uranium-237.
I don't think it's 232. I think you're very close though. I think it's uranium-233. I think it's uranium-233.
Right.
So here's where I think this fits in, right? We had our uranium-235. Here's the neutron that's about to hit it. right? That neutron got absorbed for probably a millisecond, a microsecond, a nanosecond, something like that. Promoted this instability, right? And that picture on the next slide is in between here and here. The 3 neutrons have already been ejected, but these 2 guys are still touching, right? So I think it's actually uranium-233 at the moment. Now, I like this picture a lot because I can imagine if we rewind, right, just a moment, right as that single neutron was hitting the uranium-235, I bet that it hit roughly in the middle, like maybe up here, or maybe it hit exactly in the middle, but was kind of hit at an angle, right? So that neutron got in there a little bit, but ended up causing some kind of jostling around of the protons and neutrons that were there. And it ended up creating a region that was a little bit thinner. So if we imagine that originally this was like a sphere, that neutron got in there and it caused a region of the, it caused the entire nucleus to be a little bit thinner in the middle than it used to be. It's a little bit thinner than it used to be, right? We don't have all of these nucleons and these nucleons that used to be right next to each other. They're not touching anymore. And any strong nuclear forces that existed between like these nucleons and these nucleons, they're not there anymore. The strong nuclear force was a really short-range force. So any strong nuclear force that was with these ones and these ones a millisecond ago when they were touching is gone. Is the repulsive electrostatic force gone between these ones and these ones? No. No, that's a longer range force. So as soon as we get them to separate a little bit, just to even allow the entry of that neutron that promoted this, we now have an electrostatic repulsion. We have an overall repulsion. And as soon as we do that, we're not getting those back together, right? They're going to accelerate apart. They're going to accelerate apart, and both of these fragments, right, will end up moving. They're not just going to stay sitting there. They're going to move away from each other. And then these neutrons got ejected because the way that I'll say it is they got ejected because they're just not needed. Right? We now have 2 smaller nuclei. We don't need as many neutrons per proton for a smaller nucleus, so those neutrons got ejected. But these guys are accelerating away from each other. When are they going to stop accelerating away from each other? When they hit something. If we're dealing with uranium-235 and nuclear power plants, what are they likely to hit? Another uranium-235, right? So I mean, in a uranium-235 pellet, we have billions and billions of uranium atoms in solid form, so they're very closely packed, right? So we have, it's usually uranium oxide, so we'll have actually uranium and oxygen ones. But if this one fissions, right, and these 2 fragments accelerate away from each other, that's going to cause a collision, right, with the atoms next to it. And then guess what that produces, because of that collision? Heat. Yeah, it gets really, really, really hot. That's how we generate electricity. The fuel gets super hot. That makes water adjacent to it super hot. We let that water gets way hotter than the boiling point. We just keep it under really high pressure. But then we use that superheated water to boil some other water and then drive a turbine. That's what we're going to study next topic. But yeah, we release a tremendous amount of thermal energy, which we can harness to make power. All right, so I think this diagram tells a much bigger part of the story than the cartoon on the previous page. So anyway, we're gonna quantify this more later, but questions at this point about this neutron causing that instability, and then once we create these 2 proto-nuclei, right, then they're going to accelerate away from each other. Questions about that? All right. So yeah, Elizabeth.
Would the neutrons that are going away from this reaction and coming together atoms also cause similar?
Yeah. So what's happening with these? What will these neutrons do? They could hit another fissionable isotope and cause fissioning, but as it turns out, it's actually really difficult to get them to promote another fission. We need a special part. We need a special component of a nuclear reactor called a moderator, which needs to slow them down in order to lose energy to promote another fission. When they get emitted, they have too much kinetic energy and they just shoot right through. if they encounter another uranium-235. We actually need to slow them down to get them to cause a fission. But they can do that. And then we also have to have parts of our plant to make sure that not too many of them do that all at once. Because if too many of them do that, well, what do we have instead of a power plant? We have a nuclear weapon. Well, we might have a meltdown, but no, worse than that, we might have a nuclear weapon. So yeah, they can, if we're smart enough to get them to, but we need to make sure that only a few of them will cause more fissions. But again, that's exactly where we're going in topic 8 when we look at turning nuclear energy into electricity. All right, so let's briefly talk about fusion, and then we'll change gears, right, and come back and quantify this stuff. So fusion is the exact opposite. We have two smaller things, and we shove them together and then create a bigger nucleus out of it. So the example that we're looking at here is our heavier two isotopes of hydrogen. So we have deuterium, which is hydrogen with 1 neutron, and then we are attempting to fuse that with tritium, which is hydrogen with 2 neutrons. And if we're successful, we're going to build something bigger, and that something bigger would most likely have 2 protons and 4 neutrons. So that's helium, and then, at least in this example, we're getting a single neutron ejected from that as well. Now, to make this happen, we generally need super high temperatures and pretty darn high pressures. The reason we need super high temperatures is that these things attract each other, right? No, they don't attract each other. They actually repel each other pretty strongly once they get close, because this has a positive charge and this has a positive charge. So we have an electrostatic repulsion, and we're not going to have strong nuclear force until these are touching. So in order to even get these close enough for some strong nuclear force to exist, they need to be moving crazy fast. Right? Super high speed, super high kinetic energy, or else they will move away. The repulsive acceleration will cause them to move away from each other before they come into contact. So we need super high kinetic energies. That means super high temperatures. Right? Temperature is a measure of the molecular kinetic energy. So we have super high temperatures and then super high pressures because we want these guys to have a reasonable likelihood of coming near each other. If we have low pressures, then we just don't have very many molecules. So we want lots of molecules to promote the possibility of the fusion. Now, I'm not going to lie to you. It is possible to do fusion at colder than super high temperatures. That's called cold fusion. But I mean, we are nowhere close to making energy with high temperature fusion, and we're even further away from doing cold fusion to generate electricity. So we're not really going to consider cold fusion in here. All right, so we usually need very high temperatures, very high pressures. We can do it, like in right outside of Princeton. The Princeton Plasma Physics Lab is one of the Department of Energy sites that spend a lot of money to do this, but nobody can do it yet and make it economical. Yeah.
So what would the potential applications be?
What would the potential what be?
Applications.
Well, we want to make electricity with it.
So it's the same thing as but why would we want to, what's wrong with fission?
What's wrong with fission? So the biggest thing that's wrong with the biggest thing that's wrong with fission is the uranium-235 is actually not. It's pretty stable. It has a half-life. I don't know what the half-life is. I want to say it's 4 billion years, but that might be a different isotope of uranium. But a lot of these guys, a lot of the things that are produced during the fission are highly radioactive. All right, that's not good. We don't want that stuff. Right?
Okay, so that's
We
what
gotta do something with it.
radioactive
It's
waste is.
dangerous. Right, so it's the radioactive waste, or if somehow the stuff gets out of the plant, like happened in Japan just a few years ago, I mean, then we're breathing it in, we're eating it, right? We're drinking it, if it's in the water, that's very problematic. With fusion, right, and this, to my knowledge, this is the fusion reaction that most people are trying to make economical. Deuterium is very stable. Tritium's not the most stable stuff in the world, but it has a half-life. Well, you've got your beta decay thing with tritium. It was like 12 years. 12 years means it's not very radioactive. right? There's not very many counts per minute, even when the sample's fresh. If it takes 12 years for half of the sample to decay. And then this stuff's, well, this is extremely stable. This is not very unstable, but the decay mode isn't dangerous. So we have no like radioactive stuff here. And that's why we want to do it instead of fission. Justin?
Is it also like you have a lot more abundance of hydrogen atoms, and it could be
Yeah, well, we do have lots of regular hydrogen, and I don't think it's super expensive to create this stuff, but I'm not sure. But uranium-235 does cost some money to enrich the fuel. Nick?
What's the half-life of the products of fission?
Well, I can't really say because we don't always get the same products, right?
For krypton.
I have no idea. We can look that up later on, but I have no idea. But many. Did I already make your notes for Friday? I think I may. If I did, I'll pull one thing up. No, I didn't. I was looking. Yeah. If I had your notes ready for Friday, I could show you one little chart that'll be there, but I just don't have them ready yet. All right. So that's fusion. And again, we're trying. We've been working on fusion just as long as we've been working on fission. But fission we've been producing commercially in this country since the 1960s. Fusion we're still not. Ever since the 1940s, we've been 50 years away from generating electricity with fusion. Right. So in 1940, they said in 50 years we'll be doing it, and still in 2014 they say in 50 years we'll be doing it. So I guess you could say we've gotten nowhere. So anyway, we're not done talking about fission and fusion even in this topic, and then we do talk about fission a whole bunch more in the next topic. But all that we'll continue to do in topic 7 is calculate the energy release. This one actually is almost diagrammed for us. And then in the next class we'll take a closer look at fusion in the sun. Right? So David gave us a good precursor of that, but we will be a little more specific about what or how the sun is doing this and what the other steps are, because it's not just as simple as taking 2 hydrogens and making a helium. There's more steps than that. Yeah.
Can I get a question? During
Why don't,
presentation?
yeah. So just hold on a minute or two. I'll get the sign-up sheet out. Other issues right now on describing nuclear fission or nuclear fusion. All right, great. So let me stop recording. We'll bring Cliff and Emily up.